For exercise 8, let's dial it back just a little bit back to the very first lesson that was in this module. In this unit, consider region R bound below by the curve f of x is equal to x squared minus 1 here. I got a picture of that for you. Okay, and above by the curve, it says a curve, but it's pretty much a straight line, which you can consider a curve, you know, from a certain perspective. There you go, it's x plus 1. And we want to find just the area of that thing. There's no volume just yet. So remember that what I suggested that you do, and the payoff is in this lesson, is to draw in a representative rectangle. So that's what I'm going to do. So we would have partitioned that whole entire thing, and then here is one of those little sub-intervals turned into a rectangle. And, you know, that definite integral basically adds up an infinite number of those things. So let's go ahead and find the area between these two curves. I'm going to go with, for this section, how about this nice purple color right here? All right, and then maybe I even colored this thing in. Should I color it in purple too? Okay, all right then. I'm listening to you. Look at that. I didn't even color outside of the lines. It's glorious. Nope. All right, so how do I find the area between the two curves? With my representative rectangle, I just need to find the length of this thing. So the length of it is the top minus the bottom, remember? And, well, that looks terrible. Let me rewrite that. What is going on? Just kidding. I can erase it pretty easily. Bottom. And our top function, I do believe, is the line, which is our g of x function, g of x. And then our top function, our bottom function, of course, is our f of x, which is our line that is right there. Okay, and then I'm just going to integrate that, top minus bottom. So it would be the definite integral from, oh, I don't even have our little points of intersection. I can see pretty easily here. I could set them equal to each other here, but that's at -1 on the far left-hand side, and then over on 2 on the right-hand side, right? Again, if I didn't have a picture of the graph, I can very easily just set these two equations equal to each other and find the points of intersection there for my bounds of integration. All right, so inside here, we just want to do a g of x minus a f of x dx. Now, the point of the rest of these videos are not necessarily to find the exact answer here, is just to be able to set it up and then make some relationships between these two things. So once again, we got a top minus a bottom, and then you can easily just substitute in each one of these functions here, integrate that. It'd be pretty easy to do. Okay, so let's see how this now applies to this new generalized volume using similar cross sections. Let's go to exercise 8 here. So it's the same exact region, but now we're going to say that that particular region is the base of some sort of solid. And we want to find the volume of this solid formed by square cross sections, and each one of those square cross sections is going to be made perpendicular to the x-axis. So they usually tell you that it's going to be, I say usually, they always tell you that, perpendicular to the x-axis. So then you have vertical representative rectangles are perpendicular to the y-axis, in which case you would have horizontal representative rectangles. Pay attention to that, right? Okay, so imagine, if you will, that this slice here is the bottom part of, it's basically a square prism, and it's going to come out at us on a three-dimensional axis, a z-axis, and then here's one of those slices. And if I want to find the volume of this, once again, it is basically a prism. I find the area of the cross-sectional face there, and then multiply it times its width. To find the area of a square, it's just side squared, so we just need to figure out what this side of the square length is, and that's pretty easy because we already did it. It corresponds to this piece here. It's the top minus this bottom, and we said this top function is the g of x function, and the bottom one is the f of x function, so it's g minus x. And then notice that the height of that square, since it is a square, should also be g of x minus f of x. So however wide it is, that's how high that solid is going to be, the distance between those 2 points on the function. And then our width for that piece, of course, will be our delta x. We have a change in x for our partition there, all right? So in order to find the volume of this thing, we find the area of this cross-sectional piece and then multiply it times dx in our definite integral. Whoops, all right, so let's do that over here. and see how that compares to the one that we just found. So this is going to be our side length. This is our S here. And then to find the area of a square, I think you remember the formula as just that side length squared, right? So remember our generalized volume formula goes definite integral from a to b, area of your cross-sectional piece with respect to x. So think of it like this, will ya? Let's go over here to red. But this has a unit squared on it, right? As far as its units for the area of that cross-sectional face. And then dx, its units, it's x, that'll just be in units. We multiply those things together and we have our units cubed, which is going to be our volume, right? The same thing happened with the ones with the disk method, because this would have been pi r squared, which has a unit squared with respect to x, whoops, dx, which is also a units, multiply those things together and you get your units cubed. Okay, so let's continue with this particular one, which we're going to put our side length squared inside of our definite integral, and here's what that thing is going to look like. Definite integral from, and it's the same exact limits integration here. We got -1 over here on the right-hand side. We got 2 over here on, I said right, I meant left and right, -1 and 2. Yeah, there you go. We said our side is g of x minus f of x, and then we're just going to square it because that's how you find the area of a square, pretty sure. So it's g of x minus our f of x squared dx. And then you can see how that compares very favorably to the one that we just found. Again, it's a top minus bottom, but it was just area, so we didn't have to square that thing. And then here are square cross sections. Top minus bottom, once again, to find the side length of it, and then square it because that's the side length squared with respect to x. Now, as far as finding this like by hand, if you had to integrate this, especially since you have this function minus that function inside here, you wouldn't be able to do u substitution because you don't have anything in here. You'd have to actually expand this thing out by squaring whatever you had inside, and then term by term take the definite integral. Or alternatively, you can just plug that whole thing into the calculator. All right, I have a model for this. It's pretty interesting. Maybe shed some light on this whole entire process. Let me switch once again over here to the camera view so we can take a look at it. It's much more delicate of a model than the last ones. All right, so here we go. So I'm going to kind of get a top-down view of this thing. All right, so you can see that we have that parabola that is down there at the bottom, and then on the top we have the image of the line there. Whoops, and then let's look at this in 3 dimensions. Look at this. Rotate this thing around. So we can see if I take out one of these little squares here that fits in there very nicely, the distance between those 2 points on our curves becomes the side length for that particular square, okay? And then the same thing is true about all of those little cross-sectional pieces.